Just to clarify, down, up is 1.
Correct. All right, go ahead, lift off. And on your beat, go ahead. All right, Leah, that's out.
Yeah.
I'm done.
I don't know what that sound was. Okay, that's enough.
You got 23. Yes.
Okay, and go. Okay, I got kilos 39. 39.38. He's just over there doing his thing. 40. Okay. And 38. Okay, we can stop that video. Stand up. And down. Okay. Are you ready? Go.
There we go. 24.8. A little more.
Lower. Lower. There you go. Yep.
3, 2, 1. There you go.
13.9.
Okay, when you guys are ready. Take a few seconds and we'll do trial 2. Remember your numbers. Okay. You can go first. Okay. 17.7.
on. Stand still. Good position. 3, 2, 1, pull! Right.
Now that you've seen what the isometric mid-dipole test looks like, we can begin to look at the results. And using this sample results of the raw data or the actual plotted force plate data, I will guide you through the steps to be able to fill in the activity sheet that is posted on Canvas. So we have the initial or steady state down here. So this is going to help us to obtain the initial movement in a later calculation. We also have an identification of the peak vertical force over here. You may also notice that on this graph, the units are not necessarily identified on the axis itself, but down here underneath the x-axis with time. So here we have time, and this is measured in seconds. And the y-axis over here is newtons. So the first measurement that we are actually going to assess for the lab activity sheet is peak vertical force, so the one that's up at the top in the middle of the graph. Do note that this is a different graph from what is posted on Canvas, so you will have to go through these steps for each of those subjects 1 and 2. So here, in the benefit of using PowerPoint for this, is you can actually identify and use a ruler to draw a nice straight line from that point all the way over, and we can identify the peak vertical force. So if we look here, each of these intervals between the values is 200 newtons. So we're looking at 200 newtons each of these spots. So this line here is just below 2,300 newtons. So we're going to estimate that this one is 2,290 newtons. Now that's just a rough estimate, but we can see that there's that smaller dashed line below the black line that we drew, so we're just going to split the difference between the 2,280 newtons and 2,300 newtons. Now, in order to get the net force, we also need to subtract the initial force from there. So we're going to come down to the start of movement, and again, we're going to draw one horizontal line that crosses the y-axis once more. So here, we can see that this is about 750 newtons, so we're just going to go ahead and use that value for ease. So peak vertical force, or the net peak vertical force, is going to be the upper value, so the peak value, in this instance it's 2290, minus the stationary value, or the right before start of movement. We're going to go with 750. So in this instance, it's going to be 1540, and that would be their peak vertical force. Next, we are going to assess force at 250 milliseconds. For easy conceptualization here, that is 1/4 of a second. So we do have to use our imaginations a little bit on this one. If you're using Microsoft PowerPoint, again, you can use your handy dandy ruler and draw a straight line down to cross the x-axis to figure out what time. The vertical line we just drew is just past where 12 even would be, so we're going to go just one tick mark past 12 1/4, and this is approximately 250 milliseconds. So now that we have that, we can identify where this line intersects with the actual raw data. We can make a little circle there for our own reference. And now, once more, we're going to draw a straight line over to the y-axis for where those intersect, and we're going to go about mid-range for that line. It does intersect for quite a period of time, so we're going to estimate the middle of that. And once more, we're going to draw a horizontal line to the y-axis, and that line appears to intersect at 1,420 newtons. Once more, we need to obtain the net force here as opposed to the absolute of 1,420 newtons. So we're going to do 1420 minus 750, gives us 670 newtons at 250 milliseconds. Now that we've identified force at 250 milliseconds as 670 newtons for this example, we can use that to more easily calculate the rate of force development at 250 milliseconds. So the formula for that is force at 250 minus the force before the start of movement, which is in this case 750 newtons, so that calculation we just applied, divided by, now this is going to be translated into seconds, so we're going to go 0.25 seconds as the equivalent of 250 milliseconds. As we know, that was 670 newtons, and now we're going to divide that by 0.25, which gives us 2,680 newtons per second, which equals RFD at 250 milliseconds. Now, in order to make this a little bit easier to read as I explain the impressions or usefulness of isometric mid-dipole or similar assessments when we look at rate of force development and other similar components a little bit, I'm going to switch over here to this other doodled graph here. And we're going to look at two different profiles of possible subjects or athletes that we are working with. And what's important here is that the steeper the curve after the start of movement, or the more vertical, the better that performance variable is considered. Of these two profiles, we're going to have one that is a bit steeper. We have start of movement, 3, 2, 1, pull, 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 pull here. And then our second profile, start of movement, 3, 2, 1, pull, pull, pull. So even though these two subjects, just to demonstrate, have a similar peak force, again, this is just for demonstration purposes. You do not need to do this on your activity sheet, but just so we can have this visual to compare. So we can easily say they have very similar peak forces here. What we're really looking for at this moment for our visual interpretation is how steep this line is. Okay, so we can see here, one of these lines is definitely more steep. Once more steep is much better. The reason for this is consider elite level sprinters. We're talking about the Usain Bolts and the top Division I sprinters in the States and anybody who's really on the international circuit. We know that these two subjects here can produce a similar amount of peak vertical force, but it's important to consider the demands of the event. At top speed, so after about 50-60 meters, the average foot contact time is 90 milliseconds. So consider that is less than 1/10 of a second. That's the max or the average amount of time their foot is in contact with the ground with each stride. The faster somebody is able to produce more force into the ground, the farther they're going to propel themselves compared to a competitor who is able to produce less force in the same amount of time. So for example, let's estimate, okay, let's call this 1/10 of a second. Very rough estimation as we have no scales here. And aim for similar gapping here. Once more, we're estimating here because we have no scales on our axes. But we can look and see, comparing where the subject on the left intersects. And now I'm going to draw that same level here on the graph on the right, as well as noting where the right graph subject meets their force in that time frame. This difference here is very significant. The person on the right, or the subject on the right with the steeper curve, is far more likely to be able to win the race than the person on the left. So having that steeper curve or more Bart Simpson kind of head, if you can visualize that here, more Bart Simpson, about 4 or 5 seconds for the isometric mid-dipole, and then they are called to stop. So Bart Simpson here is much better than a more so languid hilltop kind of feature. You can also think of Bart Simpson as a cliffside versus the hilltop, because recall, steeper is better. In a bit of an exaggeration, we can compare a more hillside looking graph versus a more cliffside or Bart Simpson looking graph here. And just pretend the test ends over off to the right. The test usually lasts about 5 seconds. So peak or faster RFD, or faster rate of force development, higher forces sooner, is going to most likely lead to identifying who is going to win the race in a head-to-head battle between someone with a Bart Simpson or cliffside rate of force development on their graph versus a hillside. Now, another feature that's really great of this program is limb asymmetry. So if you look down underneath the x-axis, we can see in blue and orange we have left force and right force. Because for this test we used 2 separate force plates, we are able to measure limb asymmetry and actually have a nice visual for that. So for those of you that are looking to go into physical therapy, athletic training, some sort of rehabilitative specialist profession, this can be very helpful in determining the ability of the patient to return to play, to return to work, and if it's safe for them to do so. So we can see this lower level blue line is the left leg, or the left limb, and the orange line is the right limb. So take, for example, applying this in an ACL return to function protocol. For this subject, we can see that they have a greater reliance on the right limb than the left, which means, depending on where they are in a rehabilitation protocol, or even if they are healthy and uninjured at the time of the assessment, we can objectively identify these limb asymmetries and begin to incorporate exercises to minimize the degree of compensation, in this instance of the right leg, for the left leg.